Hi class, let's do some linear algebra. First things first, do you remember how to find the area of a parallelogram? In general, the area is going to be the base times the height. And we can make this easier to calculate by somehow giving this a frame of reference. The normal frame of reference for us is, of course, the origin and the Euclidean plane. So we're going to pretend like this point right here is the origin. Here is our x-axis. Here is our y-axis. And we're going to pretend that these are vectors. Here is vector v. Here is vector w. So, how do I calculate my base? Well, I'm going to take my vector v as my base, and I'm going to take this right here as my height. And you'll recall, just by remembering this angle, that x is going to be x over the magnitude of the vector w is going to be sine of theta. So this means that x is going to be the magnitude of w as a vector times sine theta. What we have then is that the area of this parallelogram is going to be our base, which is the magnitude of v, times x, which is the magnitude of w times sine of theta. And this, from calculus, is, of course, the magnitude of the cross product of v and w. If we put some numbers next to our vectors, so for example, say v is the vector a, b, and w is the vector c, d, then our area is actually going to be the magnitude of the determinant of the matrix a, b, c, d. Just recall from your calculus classes that the cross product of two vectors is itself a vector. The direction of this vector is perpendicular to both v and w. So when v and w are different vectors, it's perpendicular to the plane defined by v and w, and its magnitude, the magnitude of this vector, is the area of the parallelogram defined by v and w as above. Let's see if we can think about this in 3D. In 3D, 3 dimensions, say v is the vector a, b, e, and w is the vector c, d, f. Then we know from calculus that the cross product of these two vectors is going to be the determinant, as we know the determinant of I, j, k, these vectors, and the transpose of v in the first row and the transpose of w in the second row. We can get a visual on what's going on just by doing this example where e and f are 0. This pushes it back into the xy plane. Let's do this calculation. So AB 0, CD 0. If we were actually going to take the determinant of this, we could use the third row. The third column. Starting with this k, erasing that and that, we're going to get the determinant of A, B, C, D times k and a bunch of zeros, of course. This is just the determinant of A, B, C, D times k. K is in the direction perpendicular to the xy plane where A, B, and CD live. This determinant is going to be the signed area of the parallelogram determined by A, B, and CD. To just draw us a little picture, we've got our xy plane, say here are two vectors. They determine some kind of parallelogram. And we've noticed that our vector, our cross product, will go in the direction of K, which is in the Z direction. What if we're not talking about parallelograms, but the three-dimensional analog of parallelograms? So let's look at a parallelepiped. The parallelepiped determined by ABC, DEF, and GHI. So let's just say that these are the three vectors that are determining this parallelepiped. And the volume of this is going to be the determinant of A, B, C, D, E, F, G, H, I. Here's what I want you to do. I want you to think of the determinant of the matrix whose rows are n by 1 vectors transposed. Think of this determinant as the signed area if you're in 2D, volume if you're in 3D, or the n-dimensional volume if you're in higher dimensions. Think of it as the signed area or volume of the higher dimensional parallelepiped determined by those vectors. This is going to help us with our geometric interpretation of the determinant. Let's explore some examples. Say I'm looking at the matrix I, and I know how to find the determinant. It's 1. But instead of thinking about this this way, our old way, think about the rows, our vectors that determine a cube of side 1, side length 1. We know how to calculate the volume of a cube of side 1. It is 1 by 1 by 1. And so the determinant is the signed volume. If I were to think of 2, 0, 0, 0, 2, 0, 0, 0, 2, okay, this should correspond to a cube of side length 2, like so. We know how to calculate that volume. It is 2 by 2 by 2, which is 8, which actually coincides with the determinant. We can extrapolate to things that aren't cubes. The determinant of a diagonal matrix is the product of the diagonal entries. As you know, so for example, 8, 0, 0, 0, 2, 0, 0, 0, 3. This is going to be 8 by 2 by 3, which is 48. We can instead think of this as simply the volume of an 8 by 2 by 3 box. 8 by 2 by 3. After building some of this geometric intuition, we can actually start playing around with some of the different claims that we proved about determinants and seeing if we can understand them geometrically. For example, here's a question. What if one of the sides of our boxes, parallelepipeds, cubes, parallelograms, etc., what if one of the sides collapses into the others? For example, say A is 2, 1, 4, 2. This is, of course, a matrix. I want you to start thinking about it in terms of the rows. We've got the vector 2, 1 and the vector 4, 2. Here's what you might notice. 2 times the vector W is equal to the vector V, which means that if we were to sketch this really quickly, if this is V, then W is here. W is in the span of V. V and W are not linearly independent. They are linearly dependent. And this is because V, we can see this because V minus 2W is equal to the 0 vector. All right, but let's talk about the parallelogram. The parallelogram defined by these two vectors has no area. So even without calculation, we know that the determinant of A should be 0. Let's do another example. Example, if A is equal to 2, 1, 3, 4, 3, 7, 1, 1, 2. We can think of this as a matrix, of course, but we can also think of this as 3 vectors, V, W, and U. Notice W is equal to V plus 2U. If I were to sketch this, if this were V and this was U, then we can add another U to this. Boom, 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 boom. This vector here is going to be W. V, W, and U are not linearly independent. They are linearly dependent. Negative V plus W minus 2U is equal to the 0 vector. The span of V, W, and U, even though it's 3 vectors, it is not 3-dimensional space. It is not a 3-dimensional parallelepiped. It is a plane. So the parallelepiped has no volume. So even without calculation, we would expect that the determinant of A is going to be 0. And so it is. Let's look at some of our claims from earlier lessons. Claim 12, if you remember. If A has a row or column consisting entirely of zeros, then the determinant of A is equal to 0. Recall also claim 13. If A has two identical rows or columns, then the determinant of A is also equal to 0. Here's the idea. Geometrically, the parallelepiped, I'll put this in quotes because it might have multiple dimensions, the analog of the parallelepiped, defined by the row vectors, much like the examples that we did before, has no volume. There aren't enough dimensions. And so the idea behind all of this, behind these two claims, is that if the rows or columns of a matrix A are linearly dependent, then the determinant of A is equal to 0. Both claim 12 and claim 13 are examples of this phenomena. We're going to actually prove this later, but for now, let's continue with our geometric interpretations of our determinants and our geometric interpretations of our older claims. Let's revisit our elementary matrices. Recall claim 14. If E1 is an elementary matrix of type 1, that means it's an elementary matrix that switches rows, and A is an n by n matrix. Then the determinant of E1 times A is equal to negative the determinant of A. Here's the idea. Changing the order of the vectors in a cross product changes the direction of the resulting vector by the right-hand rule, of course. So say I've got my vectors I, j, and k. Well, we know that I cross j, for example, is k, but j cross I is negative k. In general, v cross w is equal to negative the vector w cross v. However, two vectors determine the same parallelogram no matter what order we put them in. So, switching two rows of a matrix will switch the sign, but not the magnitude of the determinant. That's the idea. Let's revisit type 2 elementary matrices. Recall claim 15. If E2 is an n by n elementary matrix of type 2, that means it scales a row. Let's say it scales row I by some non-zero scalar alpha. If A is, of course, another n by n matrix, we have previously shown that the determinant of E2 times A is equal to alpha times the determinant of A. And this one is pretty easy to kind of imagine what's going on. Here's the idea. Say I've got, let's stay in 2 dimensions, and I've got some parallelogram determined by V and W. What if instead one side was alpha times V? I would get a new parallelogram. If we scale one side of the parallelogram by alpha, it should scale the area by alpha. General idea. Let's revisit type 3 elementary matrices. Claim 17. If E3 is an n by n elementary matrix of type 3, that adds some scalar times rho I to rho j, and A is some other n by n matrix, then multiplication by E3 does not change the determinant. Here's the idea. Let's set this up. Say I've got my 2 vectors. Here's my vector V, and here's my vector W, and they determine some kind of parallelogram. All right, well, let's see what happens if we think about alpha times V. Parallel to V is going to be alpha times V, which means that going from here to here, just by the addition of vectors, is going to be W plus alpha times V. So now we've got V, we've got W plus alpha times V, and we've got a new parallelogram that it defines. Recall how to calculate the height. Well, how to calculate the area of a parallelogram. The area is equal to the base times the height. The base is still vector V, the magnitude of vector V, times h. And so the area hasn't changed. So the determinant hasn't changed. All of this was meant to give you an idea about the geometry of the determinant. I do expect you to have some lingering questions, some of which I signaled will be important later. So number 1, yes, I gave you an idea. Can we make this rigorous? We can, but I actually think this will build a strong intuition for you, and that intuition will work wonders in moving forward. So we can make all of this rigorous. we will not make this rigorous. But what we will revisit and what we will absolutely prove is the relationship between the determinant of a matrix A and the linear independence of its rows. See if you can figure it out, think on this, and we'll come back to it later. See you next time.